I was thinking about this the other day. When you look at like a classic vintage bicycle, right?
Yeah.
The mechanical transparency of it is just a huge part of the appeal. Like you pedal, the chain moves, the gears turn, you can see it all.
Right. The input perfectly dictates the output, and it's
Yeah.
all just visibly right there.
Exactly. You can literally trace the entire flow of energy out in the open, but then, you step into advanced software architecture, and that totally transparent machine gets enclosed in this, I don't know, this sleek, opaque carbon fiber shell.
Yeah, which is a great way to put it, because you're trading that granular visibility for streamlined performance
Right.
and centralized design.
Right. Abstraction.
Exactly, abstraction. And that tension, between explicit visibility and architectural abstraction, that's really the defining tightrope of any major software refactor.
You're just constantly deciding what needs to be exposed on the surface and what needs to be completely hidden away in the infrastructure.
It's a constant balancing act.
Which is exactly the tightrope we are walking today. So welcome to this deep dive. If you spend your days, staring down complex code bases, or honestly, if you're just insanely curious about the structural anatomy of how high-level digital systems are actually built, we have a really phenomenal case study for you today.
We really do. It's a fun one.
Our mission today is to essentially deconstruct a single, highly technical developer diary entry. We are looking at a post that was published today, actually, August 17th, 2026.
Fresh off the presses.
Exactly. It's by a developer named Ang, and the post is titled Notes-on-Haskell-Programming, Part 215, on using custom reader monad.
And, the fact that we are on Part 215 of these notes, that tells you Ang has been at this migration for a good while.
Oh, yeah.
We are dropping right into the trenches of a very mature code base that is undergoing a serious structural evolution.
We're essentially getting to look right over Ang's shoulder at the before and after snapshots of the specific core function called parse input.
Right, parse input.
We're going to track exactly how, and more importantly, why, a programmer migrates their code from standard, direct inputs into a fully custom environment. So let's just jump right into the starting line of this migration.
Sounds good.
To understand this custom app reader monad that Ang is building, we first have to look at the architectural drag of the thing it's actually replacing, which is direct function arguments.
Yeah, because in the pre-refactor version of this code, parse input was incredibly explicit.
Like bare metal explicit.
Right. Its signature was straightforward. It was parse input, and then the types were args, arrow, IO, valid input.
Okay, so it demands its arguments up front.
Exactly. It literally will not do anything in the IO space to yield that valid input until you hand it the exact args it needs.
And Ang's notes show us exactly what those args were, too. We were talking about very specific configuration flags.
Right.
There's an input path flag, which is, telling it where the file is. There's an output format flag dictating the structure, and a tidy flag to clean things up.
Yeah, so in the old world, whatever you called parse input, you had to physically hand over that entire bundle of args.
Which, that's fine in isolation, right?
Sure, in isolation is fine. But in a real code base, parse input isn't just acting completely alone.
Right, it's part of a chain.
Exactly.
Yeah.
It likely calls a helper function, which then calls another helper function, which maybe calls a validator at the end. And if the validator at the very bottom of that stack needs to check, say, the tidy flag.
Oh man, you have to pass it all the way down.
Yes. You have to thread that entire args object through every single function signature along the way.
Even if the middle functions don't even use it.
Exactly. It's what we call parameter drilling.
Yeah.
And it creates this incredibly brittle architecture. Because if you decide you want to add one new flag to your config,
you're suddenly updating type signatures across your entire module.
You are. It's tedious and error-prone.
So going back to the bicycle, the gears are totally exposed, but they are just tangled everywhere. So Ang basically takes a sledgehammer to that old signature.
A very elegant sledgehammer.
Right, a functional sledgehammer. The after snapshot of this refactor removes those direct arguments entirely.
It's a huge shift.
It is. The new signature just reads parse input and then app valid input. That's it. The whole args arrow requirement is just completely gone.
Right. The function no longer requires you, the caller, to explicitly pass the state into it.
So how does it know what the tidy flag is?
Well, instead, the code, this is using Ang's own phrasing here, it obtains the value cleanly from the environment monad.
Obtains it cleanly. I love that phrasing.
Yeah. It achieves this localized pull using the command asks unvargs.
I actually like to think of this transition kind of like upgrading a professional chef.
Okay, I like where this is going.
Passing direct arguments is basically like handing a chef ingredients one by one for every single step of a recipe.
Right.
Like you want to chop, okay, here's the knife, you want to saute, here is the butter. The chef is completely dependent on the caller to provide the exact item at the exact right moment.
Which is terribly inefficient.
Exactly. But this new app environment is like taking that chef and placing them into a fully stocked, custom-built kitchen.
Ah, yes.
Right. Instead of standing there waiting to be physically handed the tidy flag or the input path, the function just reaches into the environment using that asks and marks command, and it just grabs the configuration the exact moment it needs it.
That analogy perfectly captures the essence of dependency injection at a functional level.
It just feels so much more self-sufficient.
It really does. And when Ang writes that the function obtains the value cleanly, they are highlighting a massive reduction in structural noise in the code.
Right, because the type signature is so much shorter now.
Exactly. By shifting from args arrow IO valid input to just app valid input, you are radically shrinking the function's surface area.
It cleans it right up.
And this is really the core utility of the ReaderT-pattern that Ang tagged in the post. The reader monad is explicitly designed for this exact kind of shared read-only environment.
So the configuration is just sort of everywhere.
Yes, it exists atmospherically. Any function operating inside that app monad can just breathe it in without having to explicitly request it in its type signature.
It creates this pristine, insulated workspace. Like, the inner functions don't even care how the arguments got there. They just trust that the kitchen is stocked.
Right, they just do their jobs.
But, and this is where the architecture hits a massive friction point, in the very next section of the notes parse input, doesn't just exist to do pure math or pure logic.
No, it has an actual job to do.
Exactly. It has to talk to the physical file system. And that pristine, insulated app environment suddenly needs a way to handle the messy reality of I/O.
And this is the central challenge of working with monad transformers like the ReaderT-pattern.
Because it's not simple anymore.
It's not. See, in the old signature, parse input operated directly in the raw I/O monad. It had unfettered access to the physical file system, the network, the chaotic outside world.
I could just do whatever it wanted.
Basically. But by enclosing the function inside this custom app monad, you've removed that direct access. You are isolated.
So you need a bridge to get back out.
Exactly.
And Ang's notes show us exactly how that bridge is built. It relies heavily on a command called liftIO.
Yes, liftIO is the key here.
Suddenly, any validation step like checking if a file exists or reading its content, it has to be explicitly wrapped. We can actually look at the before and after for the file checking.
Right, let's look at it.
The old code simply executed does file exist path, just boom, check it. But the new code, it requires liftIO and then a little left pointing triangle operator, does file exist path.
Yeah, and the file reading operation itself undergoes an even more dramatic type shift.
Because it's actually pulling data.
Right. So Ang is using a function called bl.readFilePath to pull the file content.
Okay.
Previously, that operation lived naturally in the I/O space, so it carried the type IO, parenthesis, either IO exception BL byte string.
Got it.
But to pull that exact same action into the new custom environment, its type has to change to app, parenthesis, either IO exception BL byte string.
Ah, so the IO changes to app.
Yes, and making that shift happen requires wrapping the entire read process in a liftIO triangle operator try block.
Oh, wow. And we see that same exact structural tax applied to the error handling, too.
Yeah, error handling gets heavily modified here.
Because Ang has set up some really specific, highly customized exceptions for this file parsing. Like, we're looking at a file not found path error, a general read failed path error.
Which is super helpful for debugging later.
Definitely. And there's a not text file path error, which gets thrown if the content fails and is text AC check. And an invalid EF8 exception, which triggers if it fails the ISEAC check.
Right, so very granular errors.
Very granular. And all of these use the throw.io command. But in this new app environment, every single one of those throw.io calls now demands a liftIO prefix.
They do.
So the code literally reads liftIO, triangle operator, throw.io, triangle operator, not text file path.
It fundamentally changes the visual rhythm of the code base. Every single interaction with the physical file system is now preceded by this specific operational tag.
Okay, I have to admit something here.
Yeah.
Looking at this new code, isn't adding liftIO to every single file check and every single error throw just replacing one type of visual clutter with another?
I mean, I hear you.
Like, okay, we got rid of the args parameter drilling, which is great. But now we have liftIO slapped across half the lines in the function. It feels incredibly noisy for a pattern that's supposed to be clean.
I get why it looks that way, but that visual noise is actually a deliberate architectural feature. It is not a bug.
A feature, really?
Yes. When you use a monad transformer stack, which is exactly what this custom app monad is built on, you are basically layering different capabilities on top of each other.
Okay.
The liftIO command is the mechanism that takes an action from the foundational I/O layer at the bottom and lifts it up through the stack so it can be executed inside your higher-level app environment.
So it's actively piercing the layers of the shell to get to the actual file system.
Exactly. It's poking a tiny control hole. And by forcing you to actually type out liftIO, the type system is demanding that you explicitly acknowledge the boundary.
The boundary between what?
Between pure calculation and messy reality. When you see liftIO does file exist, it acts as a structural warning label.
Oh, that's interesting.
Right. It tells any developer reading the code, attention, we are temporarily leaving the safety of our custom environment to query the unpredictable external world.
Because the external world fails all the time.
Constantly. A file might be missing, which triggers your file not found exception, or the encoding might be completely corrupted, triggering the invalid F8 error.
Right.
By tagging these operations with liftIO, you are completely isolating your side effects. You can look at the function and instantly visually parse which lines are safely reading from the pure and vargs environment and which lines are risking an interaction with the disk.
So that's like a hazard sign.
Exactly. That explicit demarcation is just the toll you pay for the broader safety of the ReaderT-pattern.
Okay, honestly, that makes a lot of sense. The environment gives you clean access to your state, and liftIO safely manages the inevitable incursions into the real world.
Exactly.
But this actually brings us to a massive ripple effect in the architecture.
Right? Because we aren't done yet.
No, we aren't, because if we've completely changed the internal mechanics, swapping direct arguments for an environment and swapping raw I/O for lifted operations, then the way we actually boot up and test this code has to be entirely rewritten too.
Oh, yeah. The execution boundary must evolve to support the new interior. You simply can't change the engine without changing how the ignition works.
I love that analogy. And Aang documents this final phase of the refactor by showing us the test wrapper function.
Right, which is crucial for making sure this all actually runs.
So the wrapper is called run parse input. Its dedicated job is to run our new parse input function and catch any of those specific appers we just talked about.
The not text files and invalid if8s.
Exactly. It catches them and safely packages them back into an either type result.
Which, just for context, is standard functional practice at an execution boundary.
Right.
You want to execute the risky operation, trap the custom exceptions, and then collapse the whole result into an either. That way the rest of the program can pattern match on a clean left or right, rather than dealing with unhandled runtime explosions.
Right. You want to fail gracefully, but the actual execution syntax is what's really fascinating here.
Let's look at the difference.
Before the migration, executing it in the test wrapper was incredibly trivial. The old code just evaluated, try, parenthesis, parse input, args.
Super simple.
You just threw the bundle of arguments at the function and let it rip. But now, the signature changed. It doesn't accept args directly anymore.
Right, it rejects them.
So Aang notes that they have to wrap the execution with a brand new helper function, and this one is called runapp.
Right. So the execution line lengthens slightly to accommodate this new reality. It becomes try, parenthesis, runapp parse input args.
So runapp is the new key.
Yes. Aang explicitly notes that this helper function is injected to provide the necessary custom app monad environment.
So if we go back to our analogies, think of this runapp helper kind of like a clean room airlock.
Oh, I like that.
You can't just run parse input out in the open anymore because it requires that fully stocked custom kitchen we talked about.
Right. It expects things to be in the air.
Exactly. So you have to boot up the app environment first, and that's exactly what runapp does. It boots it up, and you inject the args directly into that airlock.
Yeah.
Once the airlock is pressurized with the configuration, then parse input can run seamlessly inside of it, just pulling whatever it needs via asks on vargs.
That is exactly how it works. And this test wrapper fundamentally synthesizes the entire point of the refactor.
It really brings it all together.
It does. Think back to where we started with the notes. The disappearing arguments.
Right.
We removed args from the inner parse input function. But data doesn't just vanish into thin air. The program still fundamentally requires an input path and a tidy flag to actually execute.
They didn't disappear, they were just relocated.
Exactly. They were pushed to the absolute perimeter of the program. You see them right there at the execution boundary. Run app, parse input args.
They're right at the edge.
And this is really the hallmark of advanced functional architecture. You push the state, the configuration, and the messy setup to the very edge of your system.
So the middle is clean.
Exactly. By centralizing the environment injection at the run app boundary, the vast majority of your interior domain logic becomes completely decoupled from the mechanics of how the data was gathered in the first place.
We successfully enclosed the vintage bicycle.
We did.
The interior functions are just humming along in their carbon fiber shell, blindly trusting the app environment to hold the data they need.
And trusting the liftIO boundary to handle the physical reality of the disk. It's really a masterclass in separating concerns.
It really is.
The configuration is handled at the edge, the state is read from the ether, and the physical execution is tightly controlled.
So just to pull all of these threads together for you listening, we have witnessed a massive structural shift in part 215 of Eng's notes today.
A lot of ground covered.
Yeah. We started right at the type signature, watching those direct function arguments vanish. arg's arrow IO was replaced by the streamlined app environment, which allowed the inner functions to totally eliminate parameter drilling.
They could just pull what they needed via asks and vargs.
Exactly. We then explored the operational tax of that isolation. We analyzed how the liftIO bridge was erected to safely penetrate the monad transformer stack.
Right, we watched it actively wrap those file system checks.
And specific exception throws, like invalid F8 and not text file, which forced the developer to explicitly acknowledge the boundary between pure state and physical I/O.
The hazard signs.
The hazard signs, exactly. And finally, we arrived at the execution boundary itself, looking at the run app airlock.
Where it all comes together.
We saw how the run parse input pest wrapper cleanly supplies that app environment at the exact moment of execution. It catches those app errors into an either type and proves that the arguments didn't vanish, they just moved to the perimeter.
It is a highly effective demonstration of why the ReaderT-pattern is so incredibly prevalent in production Haskell codebases.
It really is.
Because it trades that upfront architectural complexity for long-term maintainability and localized reasoning.
Right. But, as we wrap up today, I actually want to leave you with a provocative thought about that exact trade-off.
Oh, let's hear it.
Because we've spent this entire time praising the elegance of hiding the direct passing of arguments, right? Allowing functions to simply ask the environment for their needs.
Yeah.
But I want you to consider the perspective of a brand new developer joining this team tomorrow.
Ah, the onboarding friction.
Exactly. Because when you look at the old parse input signature, you knew immediately without reading a single line of the actual function body exactly what inputs it required to run.
Right, the signature was an explicit contract.
But now, with parse input app valid input, that immediate clarity is completely gone. To know what configuration flags the function actually uses, you have to read the internal implementation. You have to hunt down the asks and vargs calls.
You had to dig for it.
Yeah. So in our quest to eliminate parameter drilling and build this sleek carbon fiber shell, are we trading the immediate discoverability of our code for architectural elegance?
That's a real question.
When the function no longer advertises its dependencies right on the tin, do we make the system harder to intuitively grasp for the uninitiated?
It's the double-edged sword of abstraction.
It really is, and it's definitely something for you to mull over as we wait to see what architectural evolutions Eng tackles in the next post. But that's all for today. Thank you so much for joining us on this deep dive into the anatomy of a refactor.
It was a great one.
We will definitely catch you on the next one.